Welcome to today's in-depth discussion, where we explore a cutting-edge development in artificial intelligence, specifically within the field of computer vision. We're talking about the latest model from Google DeepMind called TAPIR, or Tracking Any Point Within Per-Frame Initialization and Temporal Refinement. If you're interested in delving deeper, you can find the link to the research paper in the description below. Computer vision, a fascinating offshoot of artificial intelligence, is designed to emulate our human ability to perceive and understand visual data. It enables AI systems to extract meaningful information from images or video footage, to identify objects, faces, or scenes. The technology has seen widespread application across various sectors like security, healthcare, education, and entertainment, to name a few. The engine driving these sophisticated visual recognition tasks is a method known as deep learning. It allows computer vision systems to learn from enormous volumes of data and identify crucial features needed for specific tasks. Take facial recognition as an example. The AI needs to discern unique traits, such as the contour of the eyes or the shape of the mouth. However, a significant challenge arises when these systems attempt to track a specific point in a video sequence. Whether it's following the tip of a person's nose or the center of a pupil through a video, it's a complex task. Why? Because it has to deal with various elements like occlusion, or where the point is hidden, motion blur, changes in light, or even variations in scale. That's where TAPIR steps into the spotlight. This innovative model demonstrates exceptional proficiency in tracking any point on moving objects with precision. It does so by harnessing deep learning techniques and integrating two mechanisms: per-frame initialization and temporal refinement. TAPIR is trained to understand the complex dynamics of moving objects, adjusting to issues like occlusion, lighting changes, and scaling variations. By refining its tracking process over time, TAPIR achieves a higher degree of accuracy and consistency, making it a reliable model in the rapidly evolving field of computer vision. The potential implications of TAPIR are indeed far-reaching. For instance, in security applications, TAPIR could enable more precise tracking of individuals or objects within surveillance footage. In entertainment, it could revolutionize special effects or make virtual reality experiences even more immersive. For education, it could enhance interactive learning platforms by analyzing students' movements or gestures. And in healthcare, TAPIR could potentially transform surgical procedures by tracking anatomical landmarks or assist in patient rehabilitation by monitoring movements. Let's now talk about the development of the TAPIR model. TAPIR is a product of a collaborative effort between Google DeepMind, the VGG Department of Engineering Science, and the University of Oxford. It introduces a two-step algorithm to revolutionize how we track points in videos. Intrigued? Let's delve deeper. TAPIR's two-stage algorithm is elegantly simple yet profoundly effective. It comprises two stages, a matching stage and a refinement stage, each tackling a different facet of tracking. During the matching stage, TAPIR peruses each video frame independently to locate the most suitable match for the query point. The query point, you ask? This refers to the specific point we want to track through the video sequence. For instance, the tip of a person's nose. To find a match for the query point in each frame, TAPIR employs a robust deep neural network. This neural network ingests an image patch surrounding the query point, transforming it into a feature vector that encapsulates the appearance attributes of the patch. Through this feature vector, TAPIR can capture the salient visual characteristics of the query point. The model then measures the similarity between this feature vector and those from all potential points in each frame, using cosine similarity as the yardstick. The point yielding the highest cosine similarity score is christened the candidate point match for that frame. Thanks to this matching stage, TAPIR can independently pinpoint the most probable match for the query point in each frame, ensuring robustness against challenges like occlusion and motion blur. Consequently, even if the query point gets partially hidden or blurred in certain frames, TAPIR can still identify the best approximation based on the visible characteristics. This stage is paramount for maintaining tracking accuracy. However, simply identifying the candidate point matches doesn't ensure pinpoint tracking. That's where TAPIR's refinement stage comes into the picture. It recognizes the significance of the query point's motion over time and how its appearance altered due to various factors like lighting changes or scale variations. During the refinement stage, TAPIR integrates temporal information from consecutive frames to enhance the tracking accuracy. It employs strategies like motion prediction and appearance modeling to capture the dynamic movement of the query point. By examining the query point's motion and its evolving appearance across frames, TAPIR guarantees that the track point remains accurate and robust even amid challenging conditions. Thus, the TAPIR model marries the matching and refinement stages to deliver a stellar performance in tracking any point on any surface throughout a video sequence. What's truly remarkable about this approach is its versatility. It isn't confined to specific objects or scenarios. Its broad applicability makes it a game changer in multiple domains. The team behind TAPIR published their findings on the ArcSieve platform on June 14, 2023. They also generously open-sourced the code and pre-trained models on GitHub. This move not only democratizes access to this cutting-edge technology, but also encourages innovation and advancements in computer vision, propelling the entire field forward. To clarify, the refinement stage of the TAPIR algorithm focuses on two key elements: the trajectory and the query features. The trajectory represents the path that the query point or the point of interest we're tracking follows through the video sequence. The query features, on the other hand, comprise the feature vectors that encapsulate the query point's appearance. During the refinement stage, TAPIR utilizes another deep neural network to update both the trajectory and the query features based on local correlations. This network ingests a small image patch around the candidate point match in each frame, generating a displacement vector in the process. This vector indicates the necessary shift for the candidate point match to align more accurately with the true query point. By applying this displacement, TAPIR refines the point match, moving it closer to the actual query point. In essence, TAPIR scrutinizes small portions of the image, calculates the required adjustment to sync a chosen point with a target point, and then shifts the chosen point closer to the target. This refining process is repeated across frames to polish the trajectory of the query point. Moreover, TAPIR adjusts the query features by averaging the feature vectors of the refined point matches over time. This dynamic adjustment enables TAPIR to adapt to the evolving appearance of the query point through the video sequence. By continually refining the query features, TAPIR ensures a stable and reliable representation of the query point's visual characteristics. By marrying the matching stage, which identifies candidate point matches in each frame, with the refinement stage, which fine-tunes the trajectory and query features, TAPIR achieves exceptional accuracy in tracking any point in a video sequence. Its robust adaptability allows it to handle videos of varying sizes and qualities, and even track multiple points simultaneously. This multitasking capability broadens TAPIR's utility in applications where concurrent tracking of multiple points of interest is required. In a quest to validate its robust performance, the researchers carried out thorough evaluations of TAPIR, using established benchmarks and interactive demos, demonstrating its striking capabilities. The team utilized the TapVid Benchmark, a standardized evaluation dataset explicitly crafted for video tracking tasks. The benchmark comprises 50 video sequences of various objects and scenes, each featuring ground truth annotations for 10 points per video. TAPIR's performance was then contrasted against several baseline techniques, namely SIFT, ORB, KLT, Superpoint, and D2Net. The average Jacquard or AJ metric was employed to measure the performance, which determines the average intersection over union between the predicted and actual point locations. The test showed that TAPIR outshone all the baseline methods by a significant margin on the TapVid benchmark, achieving an outstanding AJ score of 0.64. This score was about 20% higher than the next best method, D2Net, which clocked a score of 0.44. The elevated AJ score affirms TAPIR's superior ability to track points more accurately to their actual locations. Furthermore, TAPIR demonstrated exemplary performance on the Davis benchmark, a dataset specifically designed for video segmentation tasks. The Davis dataset houses 150 video sequences, each presenting diverse objects and scenes and featuring ground truth annotations for pixel-level segmentation masks. TAPIR was used to track 10 points per video on this dataset, with its AJ score calculated similarly. Once again, TAPIR came out on top, attaining an AJ score of 0.59, about 20% higher than D2Net's score of 0.39. This further solidifies TAPIR's consistent tracking capabilities across different frames. In addition to benchmarks, the team also offered hands-on demos, allowing users to experience TAPIR's abilities in real time. 2 Google Collab demos were made available, the first being the TapVid demo, where users can upload their own videos or choose one from YouTube. The users can select any point on any object in the first frame to be tracked throughout the video. TAPIR will then run on the video and display the results in real time. The second demo, the webcam demo, allows users to use their own webcam as the input source. Users can select any point on their face or any other object in their vicinity to be tracked live. TAPIR runs on the webcam feed and displays the real-time tracking results. These demos truly exhibit TAPIR's remarkable accuracy and precision in point tracking, even under challenging conditions such as occlusions, motion blur, illumination changes, and scale variations. With its ability to self-estimate positional uncertainty, TAPIR not only enhances tracking performance, but also opens up potential applications in areas like 3D reconstruction, where precise error estimation is of critical importance. In summary, TAPIR is a revolution in video point tracking. Its unrivaled accuracy, resilience, and versatility set it apart in the world of computer vision. Whether you're interested in tracking points on objects, dissecting video sequences, or delving into 3D reconstruction, TAPIR provides you with the tools to unlock new adventures and redefine the boundaries of video analysis and understanding. That concludes our deep dive into the TAPIR model. If you enjoyed this video and found it informative, please consider subscribing to our channel for more cutting-edge AI content. Thank you so much for joining us. We look forward to seeing you in our next video. Until then, keep exploring, keep learning.